Now, I'm going to go ahead and start off with our favorite slide at the summer school. And that's a slide which you've seen verbatim. I have my own version with wave numbers where I took Serena's numbers from EV and converted them to my preferred unit. So that's why they're oddly specific. But today we're going to be talking about spectroscopy in the gamma ray regime. And I think a lot of chemists are not really used to thinking about this regime. And the only real point I want to make on this slide is what is a gamma ray versus what is an X-ray? Because if you look in a textbook, you'll see that there's often a lot of overlap, there's inconsistent definitions. There's not really actually a hard and fast rule about this. The hard and fast rule of what distinguishes a gamma ray from an X-ray is that an X-ray originates from an electronic transition, and a gamma ray originates from a nuclear transition. Okay? So we're going to talk today about nuclear transitions, but we're going to use them to probe electronic structure information, because that's what we're interested in as chemists. And what's kind of the motivation for Mössbauer? Well, there's kind of a number of different effects that you'll see in spectra. There's this so-called isomer shift and quadruple splitting, which if you've ever seen any Mössbauer spectrum before, you're probably somewhat familiar with. There's magnetic splitting, and they all kind of give their own sets of useful information. So for example, the isomer shift, we can learn about like oxidation state, coordination number, etc. Same for the quadruple splitting, molecular symmetry plays a role. We can learn information about hyperfine coupling tensors if you add magnetic fields. And so there's a rich set of information we can learn that correlates nicely with other spectroscopic techniques that we have at our disposal. I hope to convince you of that today. And I had to kind of decide of the two combined Mössbauer talks that I put together. I think I had something like 250 slides. I cut out about 150 of them. We're about at 120 now. But what I cut out and what I didn't cut out was really kind of a difficult decision. And so I kind of cut out a lot of the nuclear physics. If you're interested in like how protons work and stuff, I cut all that out. And I'm just going to focus on what you really, really need to know. Okay? If you wanted, I could have a whole week summer school on Mössbauer, but we don't have time for that. And I want to give you a different view of the periodic table that I think physicists know about, but most chemists probably are not necessarily aware of. And it's kind of this weird phenomenon where, if you look by column, right, even number isotopes, they have this tendency to have more stable isotopes than odd numbers elements. That's pretty consistent across the periodic table. I'm not, just kind of squinting and hoping for the best. That's a real phenomenon. And, the question is why, This is something we don't really talk about in most chemistry courses. Why do even number elements have more stable isotopes? Even in the lanthanides, you see that. And it has to do with the fact that nucleons tend to pair up. So protons form pairs and neutrons form pairs. And if you recall, electrons form pairs. There's something fundamentally similar about all of these particles and how they pair up. That's going to become very important. And the other thing is, especially if you've ever taken like an NMR course, we kind of have this esoteric quantity nuclear spin, and it shows up in EPR, and you see something like, cobalt has like a spin, and it adds all these hyperfine lines in the EPR, but what's really the origin of nuclear spin and nuclear G factors or gyromagnetic ratios, if you're more familiar with that quantity, right? Where does that come from? And that comes from what's known as the nuclear shell model. So it's a very similar type of derivation, right, of deriving electron orbitals from a Schrödinger equation using a certain potential. This comes from what's called the Wood-Saxon potential, and if you solve it, you'll get energy levels for protons, you'll get energy levels for neutrons. And what you see is that protons pair up in nuclear orbitals. There's a 1s orbital where you can put two protons in here and pair them up. There's a 1p orbital, right, because we're solving a different potential, we have different types of quantum numbers. Don't worry about that. Worry about the angular momentum. So the p orbital, right, we know that there's 3 of those, and you can therefore put 6 protons in this level. If you turn on nuclear spin, nuclear orbit coupling, which is kind of a crazy idea, you can see that the 1p 3/2 orbital split out from the 1p 1/2 orbital. Okay, so you can put 4 protons in the 1p 3/2 level, 2 protons in the 1p 1/2 level, etc., etc. And you can fill up these nucleons in these nuclear orbitals. You can do it for protons which have their own potential. You can do it for neutrons. They start to diverge about more than 50 nucleons in terms of the exact energies because, protons have a charge and neutrons don't, right? But this is what's really cool. The nuclear shell model, which Maria Guppert-Meyer and Jan Johannes Jensen shared the Nobel Prize for in 1963. She was working on the Manhattan Project, right? These predict these magic numbers. So, why is it that a helium-4 nucleus is extra stable, right? You see alpha particles in radioactive decays because that's a particularly stable nucleus. And the reason for that is you're filling up a proton shell and you're filling up a neutron shell. So actually, helium-4 is what we call a doubly magic nucleus because you have two pairs of shells that are filled. And why is lead-208 also, the last stable isotope? Bismuth is extremely long-lived, but it's technically a radioactive isotope, right? Calcium, oxygen-16. These are especially stable nuclei because they have these filled shells, just like the noble gases on the periodic table are extra stable elements that are very unreactive. And so this also explains how nuclei can transition to excited nuclear states, right? If you do a UV-vis experiment and you transfer from one ground electronic state to to an excited electronic state, the same thing happens in nuclei, just you're promoting protons to higher energy orbitals or neutrons to higher energy orbitals in order to do those nuclear state transitions. This also explains nuclear spin. If you're an astute observer, maybe oxygen-17 has always been a mystery for you like it was for me, because oxygen-16 has a spin of 0, oxygen-18 has a spin of 0, but oxygen-17 has a spin of 5/2. Well, where does that come from? Well, you end up having an extra neutron unpaired and the 1d 5/2 orbital. Oh, 5/2. Oh, there it is. We understand why we have a certain nuclear spin. Okay? If you've ever done any sort of lanthanide chemistry, maybe you're familiar with the Landé G factor for electrons. These rules apply to nuclei too. And you can predict the G factor based on protons, these orbital and spin values. Protons have a spin G factor of 5.58. Neutrons actually have a negative spin factor of 3.82. And this is a little weird because what that means is that neutrons are fundamentally particles that are not charged but interact with an external field. But that's a property of quantum mechanics. It's intrinsic angular momentum, okay? But the orbital G factor then for electrons is 0. But you can plug and chug, and you can predict for oxygen-17 a G factor of about minus 0.765, and sure enough, the experimental, that's a pretty good estimate. So that's pretty cool. And I will admit that I'm way oversimplifying this. If you want to do iron-57, this breaks down very quickly, and you need basically a computing cluster in order to properly make those predictions. But I just want to show the proof of concept of how that all works because this is going to come up today for different nuclei. But now that we understand why we can undergo nuclear transitions, we can finally talk about the basis of the Mössbauer experiment. Nuclear resonance absorption, okay? So the idea is that you might have some radioactive source isotope that can undergo some type of radioactive decay, like an alpha decay or a beta decay, whatever, okay? And it can decay to some excited nuclear state of interest. And that excited nuclear state can emit gamma ray because it's a nuclear transition. It decays to a nuclear ground state, right? And then you have some sample which can absorb that radiation, and you can then therefore detect based on some transmittance experiment, for example, what has been absorbed, what has not been absorbed, okay? That's the basis. And this was a Nobel Prize, actually, that happened before the nuclear shell model, right? Or at least the Nobel Prize for it, I should say. And this was discovered by Rudolf Mössbauer. And what's interesting about this Nobel Prize is it's one of the few examples I know of the PhD student who did the work winning the Nobel Prize and not the advisor, because his advisor did not believe him. So if you want to win a Nobel Prize from your PhD work, just do a project that your advisor doesn't believe in, and that's the key. But the point is that this is the first ever Mössbauer spectrum, and there's kind of this weird axis velocity, which I'll talk about in a little bit. I've put an energy axis up there. That's in electron volts. I'm a wave number guy. So what I want to point out to you is that this is actually an extremely sharp transition. This is an iridium-191 Mössbauer spectrum using a radioactive osmium-191 source. And what you see is that this transition has a full width at half max of like 0.1 wave numbers. Compare that to like UV vis, where you're dealing with like hundreds or even thousands of wave number, line widths. So this is really, really sharp. Before I talk about why, let's just look at the periodic table again. This is my view as an inorganic chemist of the periodic table, right? You have transition metals like titanium through copper. You have main group, whatever. And here are the here are the elements that are good for Mössbauer. How do we know what will work and what won't? Well, we have to kind of do a number of different considerations. It turns out that you can't do Mössbauer in every single element on the periodic table. You have to fulfill a lot of different requirements. You need to have Mössbauer levels that are kind of, and I'm going to switch to keV because wave numbers are a little bit unwieldy to talk about for such large quantities, but you basically need to be between 5 and 180 keV in order to have, for practical reasons, basically like any sort of good Mössbauer isotope. You don't want attenuation or recoil energy, which I'll talk about. That's going to mess up your experiment. You need half-lives that basically allow you to do the experiment. If you're too long or short, you'll end up having problems practically with Doppler velocities or overlaps between extremely broad emission and absorption lines if you're too short. You need to have some radioactive source that's readily available, and that source needs to have a relative ease to be produced, and it needs to have a relatively long half-life. In the case of iron, we're using sources that exist on the order of a year for half-life. You need to have nuclear spin states that are congruent with what you want to do. You need to have good hyperfine coupling constant. So there's all this list of requirements, and what does that lead to? It leads to this being what's possible in Mössbauer. And basically up to americium, it's been done. This might be a little deceptive because not all of the elements are done equally, and I would say that actually maybe more than 95% of the papers are by far iron 57. Maybe the next 5-10% are tin, and then the rest of the esoteric Mössbauer world exists for the other elements. But we're going to focus primarily on iron 57 because we're focusing on transition metal chemistry, especially in the first row, and this is by far the most used and most useful of the Mössbauer isotopes because it's more or less in the sweet spot of all of our requirements. And for iron 57, I'm going to make a declaration that our velocity scale has basically about 4 × 10⁻⁴ wave number type units for every 1 millimeter per second. So just so you can keep in mind the energy range that we're looking over. Okay, this is unique for each Mössbauer isotope, but this is specific, these numbers, to iron 57. Pick whatever energy unit you want. So let's look at the decay scheme for the iron 57 experiment. We start with an I = 7/2 cobalt 57 source, which has, again, a half-life a little bit less than a year. That decays through a core electron capture into an excited I = 5/2 iron 57 nucleus. This is a nuclear state, right? And there's different probabilities to decay down to, and different pathways to decay down to the I = 1/2 ground state. The one we're interested in actually goes through this intermediate nuclear spin I = 3/2 state. This transition is about 14,000 electron volts, and that excited state has about a 98 nanosecond half-life, okay? And it's about 10% probability of happening, okay? Now, let's think about the sort of like line width, right? I told you that these nuclear energy levels are extremely sharp. And in order to understand why that is, let's think about energy time uncertainty, right? We have our time here. I'm actually going to convert it into what's called the lifetime, so you just normalize to natural log 2. But the point of that I want to make is that it has to be greater than or equal to h bar. And so you would expect a certain Lorentzian line width that will be extremely sharp, about 0.0000375 wave numbers, which is just incredibly sharp. That is the natural line width of a Mössbauer event in iron 57. Now, it's not the natural line width of what you see experimentally, and I'll talk about why in just a second, but that is the natural line width of any given emission or absorption event. Now, here's the problem. You can't just, it's actually kind of a problem, but also an interesting aspect of Mössbauer. You can't just do the spectroscopy. There's kind of a bit of a problem, and it's that the energy that's emitted when you have some nucleus, the gamma ray energy that's emitted is a lot. Okay, it's like firing a cannon, and when that happens, the nucleus actually gains a velocity opposite to the direction of the vector of the gamma photon. Okay, so it's a recoiling. You can't avoid that. So this then basically is a Doppler effect, because the gamma ray energy that's emitted, right, is actually a function of, not just the energy of the gamma ray emission, but also the nuclear motion away from that, right? And so this ends up being a problem. I'll talk about that on the next slide, I think. But you can't just emit and reabsorb high energy gamma photons, because they come into and out of resonance from this recoil energy being a problem. And so just to give you an idea, here's the gamma ray energy, and here's the recoil energy. And what you see is a delta E is here. Okay, that's the line width. I put everything in EV again. Sorry to switch between units so much, but the point is that this is 6 orders of magnitude larger than the line width. So there's just no possible way you're ever going to see anything. Okay, and so we're done. That's it. That's the end of the summer school. Except it's not, because we found a way around this. Well, not me, but smarter people than me. Right, and here's the problem, right? You think about a nucleus and some solid state lattice, whatever, right? You have some gamma ray emission, it recoils. Another nucleus recoils in the direction of the vector of the photon because it's absorbing that energy, right? So you can't get any nuclear resonance absorption to occur normally. So no gases, no liquids. But here's what's cool. This idea of phonons. This is a quasi-particle. You won't find it in the standard model of particle physics, but what you will understand is that you can kind of understand as a quasi-particle that quantizes vibrations in solids. So just like in vibrational spectroscopy, we had quantized molecular vibrations. In a solid lattice, bulk lattice, you have quantized vibrations as well that, are over the entire lattice. Okay, and so you can imagine different sorts of modes that are excited. I won't talk about, optical versus acoustic phonons, if you've ever heard of that term. But the point is this. They're quantized, but maybe they're quantized in different directions. And so, along the ith direction, the j direction, and the kth direction of your solid lattice, you might have different, kind of atom spacings and different bond strings and things like this that are going to lead to different kind of phonon wings, if you will. And so, if you kind of look at just a powder sample, right, you'll end up with like a fluorescence phonon wing, where you're emitting energy from the environment. You'll end up with an absorption phonon wing, where you're absorbing energy from your environment. And this is no different than if I just whack my hand on the table. That's a phonon exciting event. But it can also happen with light. Okay? And that light may have a scattering event where no energy is transferred between to the lattice, and that's called the zero phonon line. So you also see this extremely sharp, almost like Dirac delta type feature in the center. It's not Dirac delta, but it's extremely sharp. Okay. So we have to talk about that, because the zero phonon line is what is going to lead us to being allowed to do this experiment in solids. Okay, no gases or liquids, but in solids, we saw that zero phonon line, which means there is a finite probability that there's no recoil. Okay, this is really cool. So you can emit a gamma ray and absorb a gamma ray with a certain probability of having a zero phonon event. There's certainly a large probability in the phonon wings of fluorescence and absorption, right? But there is also finite probability of no zero phonon line, no change in energy. And the way to think about that is, okay, the lattice mass is huge with respect to one gamma ray photon. You can think of it as if, like, you fire a cannonball at the planet Earth. The planet Earth is not going to move, right? The cannonball will just bounce off it or something, or just stick against it. It's kind of like that idea. So the lattice mass is huge, maybe infinite from the perspective of a photon. So there's a probability for zero recoil in both the emitter and absorber. A more proper theoretical treatment is this, again, the zero phonon idea involves this sort of Lamb-Mössbauer factor, or recoil-free fraction, which is analogous to this kind of Debye-Waller concept that Serena brought up in her X-ray talk. But I just want to talk about phonons a little more. So here's a neutron inelastic scattering spectrum of alpha iron. You see, we're not dealing with photons but neutrons, but it's a very similar idea. You can see a fluorescence phonon wing, a absorption phonon wing, and a zero phonon line. I digitized this from the literature, so it looks a little weird, sorry. And then you can kind of create a density of states. I don't know what that analytical function might be, but it should be basically equal to about 3n, because -6 doesn't matter at such a large scale. And then we just integrate over, a frequency range from 0 up to what we call the Debye frequency of that phonon density of states, and I'll end up with, all the phonons in my solid, right? But the problem is, in most cases, we don't have like a good analytical function to describe this. So what we do is we're going to create an approximation of it and say, well, you know, it kind of increases and then drops off. And the way to do that is maybe with like a quadratic function, for example. Okay, you can basically approximate this, and this was a terrible color choice, sorry, but hopefully you can see that basically we're saying at some Debye frequency, the phonon density of states drops off essentially. And that's given by this expression here. So that's called the Debye model. And we're going to use it to approximate this phonon density of states. And the reason I bring all this up is because this is kind of the origin of a lot of the mathematical expressions that are used for modeling like how phonons and Mössbauer matter. So again, this has to do with neutrons, but you can do a similar game with using like photon scattering, kind of an idea, okay? And let me, yeah. And so often people, instead of a Debye frequency, put it in terms of temperature, so times h bar over kb. People think about this as like, this is the maximum temperature I would have to heat up the solid to basically excite all my phonons, okay? That's what that means. Now, contrasting the Debye-Waller factor that Serena talked about and the Lamb-Mössbauer factor that I'm going to talk about, I will make a public service announcement and say there's a lot of confusion between these two concepts in the literature, and people often use them interchangeably in the Mössbauer literature. But I differentiate them through a few different things. So first of all, sigma squared is a mean squared displacement derived from an ensemble average, whereas the expectation value of x squared is based on the time average. This is used to describe X-ray photon and coherent neutron scattering. This is used to describe gamma-ray photon and incoherent neutron scattering, so that's where that shows up. And finally, the Debye temperature describes the phonons of an entire lattice. We're actually going to use a related temperature called the Mössbauer temperature, but that only describes the phonons relating to the Mössbauer nucleus and has absolutely nothing to do with any other atoms in the lattice that are not involved in the experiment, okay? But very closely related ideas. And how does that, play a role in Mössbauer spectroscopy? We have this Lamb-Mössbauer factor F. That's essentially the probability of a recoil-free event. It's also called the recoil-free fraction. That's going to determine how many events are allowing you to do the Mössbauer experiment. And this is a very complicated expression that you can derive through the first type of Debye integral and all this other stuff. But all I want to point out is that, the recoil energy and the Mössbauer temperature are playing a role here, okay? And really we focus on the recoil-free fraction as a function of temperature, right? It's dependent as t squared. And what I want to show you, and as well as what's in this integral, but what I want to show you is that different materials have different Mössbauer temperatures. So for example, maybe you're dealing with a molecular complex, and if you heat it up in its solid state to 100 Kelvin, you've already excited all the phonons. Whereas maybe you're dealing with like nanoparticles or iron metal, and you would have to heat it up to about 1,000 Kelvin to excite all of its phonons in its lattice, okay? But the point is that you kind of have different regimes for like molecular compounds and frozen proteins all the way up to like nanoparticles and materials, and they have different inherent Mössbauer temperatures. You can think of the Mössbauer temperature as a sense of like a lattice bond strength, okay? This is the temperature of like a really rigidly bound lattice. You have to heat up a lot, so it's really, really tightly bound. Whereas like a molecular complex is like really loosely bound in its lattice. You don't have to heat it up so much to do these phonon excitations. But what you see is that these Lamb-Mössbauer factors, they have different dependencies on temperature. And even at 0 Kelvin, you don't ever get to 100% recoil-free events. That does not happen ever. In the case of complexes, you might get about 70% of the time. In the case of iron metal, it might be more like 97% of the time, okay? But the point is that there are differences in the Lamb-Mössbauer factors depending on the Mössbauer temperature. And the other thing that you have to keep in mind is that you want to go to as low a temperature as possible to maximize the amount of Mössbauer events happening. This is why we try to go to as low a temperature as possible in our experiment, because we want to maximize those recoil-free events. And if you do something at room temperature for a molecular compound, you're at like 5%, and you're going to be waiting like 20 weeks to get a good spectrum. Whereas if you do it at like liquid nitrogen temperature already, you're at like 25%, and you've dramatically decreased the amount of collection time you need to do to get a good spectrum. I've already talked about that. But the other thing I want to say is also about quantification. If you want to compare different species in your sample, you have to be very careful, because even at the lowest temperature, there are differences in these F factors, and you have to normalize to different Lamb-Mössbauer factors to do a proper quantification. And if you want to quantify, I would say the bare minimum temperature has to be liquid nitrogen. Really, ideally, liquid helium is the best for quantification. Anything above that, quantification is useless. So don't do it. The only time it works is if you're comparing things that are apples to apples. So if you're comparing nanoparticles to nanoparticles, it's fine. If you're comparing complexes to nanoparticles, you're going to have a bad time. Okay? So just understand that aspect. Now, what does the experiment look like? Let me just check my time. And again, I'm going to be going over time, so I'm already at 25 minutes. I have to speed it up a bit. So the experiment, and this is why we have this velocity unit scale, involves attaching the radioactive source to a Doppler drive or the Mössbauer drive, and basically oscillating that back and forth. And that's going to modulate the gamma ray energy through the Doppler effect, right? Because we can control this velocity. And then that's going to interact we're modulating the gamma ray energy with our sample or absorber, and any radiation that's not absorbed gets hit at the detector and picked up by our computer. But here's the cool part. So we have a Mössbauer emission line from the source. We have a Mössbauer absorption line and our sample. And when these are not overlapping in energy, we get almost 100% transmission. Okay, very, very little absorption. But as we modulate this energy by changing our velocity of the drive, we can start to get better overlap between the gamma ray emitter and the source, and we get more absorption, less transmission. And eventually, at the maximum of our peak, where we have a specific velocity, we have perfect overlap. Okay? And then we keep scanning until we end up on the other side of our Lorentzian. But what I want to point out is that, remember I told you about the natural line width of a given emitter or absorber? The experimental line width is twice that amount because you're dealing with two of them overlapping as they scan up past each other. So the absorber one doesn't change. We're modulating the energy of the gamma ray source only. And then you're going to see on your computer screen some gamma ray counts hitting the detector, and then some experimental line width, and then your peak will show up at some velocity. And so I told you about the natural line width earlier. Then the case of what you see experimentally, it's going to be twice that amount. So the Heisenberg line width, the quantum mechanical line width minimum, is about 0.2 millimeter per second. If you ever see a Mössbauer spectrum with a line width less than that, then the calibration is wrong, and you've violated quantum mechanics and you've won a Nobel Prize as the alternative. So don't do that. More typically, you're going to see line widths of about 0.22 to 0.3. And the reason for that is, again, talking about back to Alexander Schnegg's EPR presentation, you might have inhomogeneous broadening or unresolved hyperfine interactions. So, realistically, if I were a peer reviewer and I saw line widths like less than 0.21, I would be a bit skeptical, right? I'd be like, are you sure you don't have some calibration issue? So this is kind of the sweet spot of what you would expect. If you have line widths larger than 0.4, you probably need a reasonable explanation for that. Maybe you're dealing with nanoparticles or some distribution of chemical environments or something. You need to have a good reason for that, because typically there's no good reason for molecular species to have anything larger than that in most cases. Yeah, nanoparticles. Okay. Let's talk about the intensity of a Mössbauer spectrum. I've told you I have my counts axis, my velocity axis. And the area under the curve is basically a certain absorption, and we have, this area, and then we have some intensity where we have what we call C infinity, the counts of no transmittance, and then, 100% transmittance, and then CA, the counts, at the maximum amount of absorption or minimum transmittance. And, basically we think about normalizing this as the signal divided by the baseline, okay? And you usually see about 1 to 10% absorbance, so about 80 to 98% transmittance, since there's a logarithmic relationship between those two quantities. And I'm not going to open up this can of worms today, but we're going to deal everything with what we call the thin absorber approximation and see that everything is a Lorentzian line width. You can get Gaussians or even pseudo-Voigt line widths if you have a lot of, if you've even enriched your sample and increased what we call the thickness, but I don't want to talk about that today. But this area is therefore proportional to the number of absorbing Mössbauer atoms and the recoil-free fraction, that Lamb-Mössbauer factor. So the number of iron 57 atoms per square centimeter, that is essentially what determines this area and the recoil-free fraction. I talked about that. So for a good absorber with 1 centimeter diameter, you have about 2 times 10 to the 17 iron-57 atoms per square centimeter, so that's about 21 micrograms of iron-57 for every square centimeter. If you have just natural abundance iron is about 2%, so that's about 1 milligram sample, okay? If you do a frozen solution, you need about minimum 0.3 millimolar iron-57 to get a good spectrum. Better would be 1 to 5 millimolar. Maybe depending on the size, this depends on the size of your sample cell, but you need about, maybe a little less than a milliliter of solvent. And lastly, avoid like solvents with heavy atoms because you get mass absorption and things like this and gamma ray attenuation. So you don't want like sulfurs or chlorines are going to mess up your experiment, or at least they're going to increase the amount of time you need to collect to get a good spectrum. So those are a bit of the practical considerations of the sample. Now we're going back to this slide because now I'm going to tell you about the theory, and this is going to be intense. And I promise I will give you a break, but bear with me. We're going to talk about the origin of all of these, and then we're going to build up in complexity until you're dealing with all three at once in a given spectrum. And that's when it gets complicated, but also the most rewarding and interesting. So where does the hyperfine interaction come from? And I cut out a ton of slides with math, and I also will probably skip a lot, but I've left them in my lecture notes if you want to look through all the first principles derivations later. But essentially, we're going to derive the electrostatic energy between a nucleus sitting in its electron cloud, which is just this Coulomb constant, 1/4 pi epsilon naught, sitting out front. I'm going to call it Ke in this presentation to just knock down the number of constants I have to write out. We have a nuclear charge density that depends on the nuclear, the radius defined from the origin of the nucleus, and then we have some Coulombic potential defined by the electron cloud, and then we integrate over all space. So r squared dr, sine theta, d theta, d phi, okay? Then what we're going to do is a Taylor series expansion. We're dealing with Mössbauer, so we're going to focus only at the nucleus, so the origin. I'm going to define that as 0, 0, 0. And you end up with this crazy expansion. I promise you, though, it's actually going to become a lot more simple in about 5 seconds because what these terms are, the total electrostatic energy of the nucleus, the electric field at the nucleus, the electric field gradient tensor, and then all these higher order terms, right? Well, this first one only offsets the total energy, but in spectroscopy, we only look at energy differences, so I don't care about the first term. Oh, yeah, okay, there's actually no electric field at the nucleus, so we don't care about that term. So it's all coming from this term. I'm going to discard all the higher order terms. It's done. Okay, boom, there it is. And now we have this summation over this electric field gradient tensor, this Coulombic, this charge density, and then, this kind of dipolar type formulation, right? We can kind of expand this expression, and we end up at an isotropic component that's called the nuclear monopole moment. That is the origin of the isomer shift. Then we have another expression, the nuclear quadrupole moment. That's the origin of the quadrupole splitting, which I'll talk about later. And that's it. So I'm going to skip a ton of math, but you can bear with me that there's some reasonable things I do and not so reasonable things I do. But eventually you get to a punchline where you end up at the energy of a given electric monopole is given by, some collection of constants, including the, nuclear charge, effective nuclear charge. So, and the two key quantities I want to highlight are that this radius matters of the nucleus, but also the electron density at the nucleus, so the square of the wave function at the nucleus. Those two things are the levers that are going to control the energy of the electric monopole. So where does the isomer shift come from then based on this? For bare nuclei, you have a defined ground and nuclear excited state, not electronic. And when you put the radioactive source in a different chemical environment, these energies get changed ever so slightly. These are very tiny effects, but they do show up in the spectrum. And your absorbers in yet another different chemical environment, and its energies change. And the ground and excited state energies change by different amounts. Okay, so where does that come from? Well, the energy of the source then is going to be our gamma ray energy minus the difference in the electric monopole energies of the excited and the ground state. So that's this complicated expression here. You can simplify it a bit and see that the electron density at the nucleus of the source, okay, this is the energy of the source specifically, and then a difference in the squares of the excited state radius of the nucleus and the ground state radius of the nucleus. And fun fact, the radius of the nucleus has you can't predict that. So the excited state actually is a smaller nucleus than the ground state for iron-57. It might be different for different isotopes, and that will actually cause an inverse isomer shift correlation, but you don't need to worry about that. We can do the same game for the absorber, source, absorber. The only difference is now the wave function is corresponding to the absorber, okay? But the radii of the nuclei are the same. And then we can get to the isomer shift, which is the difference in energy between the absorber and the source. I'm going to multiply by C over E gamma to keep everything in millimeter per second units. And we end up at this expression, and we do some math, and we do some math, and we do some math. But eventually we get to this kind of collection of constants alpha, and then times the electron density difference between the absorber and the nucleus at the nucleus. That's the fundamental equation right here. I don't want to talk about that, but what I do want to talk about then is that this is kind of our final expression. And what we see then is that the origin of the isomer shift is coming from this difference in the electron densities at the nuclei and these differences in the radii between the ground and excited state nuclei. And what's the function of that? What do you see in the experiment? You see what's called the isomer shift. So you see a shift of the gamma ray energy away from the zero velocity because this is a different energy than this one between source and absorber, right? And that has to do with differences then in the electronic environment. So this is already a sensor of the electronic chemical environments of your sample versus the absorber. And we're doing everything relative to the absorber so that we can compare different samples. Or sorry, we're doing everything relative to the source so we can compare different samples because this is what changes from sample to sample. So you get different isomer shifts. Okay. And yeah, we use alpha iron foil at room temperature as our reference, but you might see different references in older literature. So now let's talk about, it's a little bit strange, but it's true. If you look at s orbitals specifically and you look at psi squared, you can look at these radial wave functions and you can see that the electron density at the nucleus, there's always antinode at the nucleus. So s orbitals have electron density inside the nucleus. That is what the Mössbauer atom is sensing. So the isomer shift is going to depend on these s orbital populations in a given sample I have. Now for iron-57, we also have other valence electrons, and it turns out you can show that 3D electrons are a little bit radially smaller, right, in their extent than the iron 3s and 4s orbitals. And so what you see is that the 3D electrons end up shielding those 4s and 3s potentials, which means that you kind of have an indirect impact where if you change the d electron count, so the oxidation state, and also the spin state matters too, right? That 3D occupation indirectly impacts the isomer shift. So this is kind of the connection between how different oxidation states, different spin states change the chemical environment felt by the nucleus, even though d orbitals have a node at the nucleus, at least in the non-relativistic limit. And this is a great paper by Frank Neza, but what he shows, right, is that the core electrons, the 1s and 2s orbitals, compared between different molecular compounds with different iron oxidation spin states, to a first approximation, those don't matter. Maybe to a good approximation, not even the 3s matters that much. It's really all about the valence contribution to a really good first approximation for Mössbauer. So these are the 4s and 3d orbitals. That is what is the key to understand why you see different isomer shifts. Okay, these core electrons are not that impacted. And so the isomer shift correlates best with covalency. I do want to make a little bit of an announcement. We use bond length typically as a proxy for covalency, but it doesn't always hold, and I'll talk about that in a second. But it's really all about covalency. So 3D valence population at the iron center, that changes the oxidation state. Bond lengths increase with 3D population. That leads to an increase in the isomer shift. Spin state, right? Low spin compounds have shorter bonds than high spin compounds because the electron clouds kind of spread out a bit, right? And so you see bond lengths decrease with lower spin states. That decreases the isomer shift. Coordination number, right? 4 coordinate compounds tend to have lower isomer shifts than 6 coordinate because steric crowding leads to bigger bond lengths and therefore a little bit less covalency. But let's think about the isomer shifts of atoms within the same row. So if I have like a nitrogen versus an oxygen versus a fluorine coordinating my center, I can clearly relate that to electronegativity and covalency, and therefore I see that fluorine, right, that's going to lead to a different isomer shift. But soft ligands like sulfur are actually more covalent with iron than hard ligands like nitrogen. So even though the iron-sulfur bond length is longer, it's actually more covalent. So don't just take the bond length too literally. It's truly about covalency. Overall, an increase in covalency leads to a decrease in the isomer shift. That's the key. And so you can kind of come up with these types of charts. I kind of updated this and adapted this from a paper, but this is sort of my own version of this. If you look up this paper, you won't see this exactly. If Sergio's in the audience, I apologize for not adding iron 7 yet, but I'll get to it one day. But right, in different colors here, I have iron 1. Those tend to have higher isomer shifts than like iron 5, okay? And orange is iron 2, and yellow is iron 3, and so on and so forth. The other thing you notice is that the spin state matters. So typically high spin states, like high spin iron 2, is going to have much larger positive isomer shifts than low spin iron 2, which might even become slightly negative depending on the context, right? And you see that there's kind of a lot of overlap here, so you have to be a bit careful in your interpretation. There's something I have to point out though, and it's something that's really, really annoying, and that's the so-called second order Doppler effect. It turns out that what you see experimentally is not just the intrinsic isomer shift, but this other contribution, which is a relativistic effect, which depends on the mean squared velocity of the Mössbauer nucleus. And I don't want to get into it too much, but you can again kind of use the Debye model and use the Debye integral of the third kind to talk about this. But if I have some intrinsic isomer shift, let's say of 0.4 millimeter per second, depending on the Mössbauer temperature of my sample, that will become a temperature-dependent quantity as well. And this is a negative quantity, so this works against the intrinsic isomer shift. But what you'll notice is that as I go to higher temperatures, by the time I'm at room temperature, if I have like a molecular compound, transition metal compound, I might be 0.2 different. That's huge, and that is going to affect our interpretation of the oxidation spin state. And that is no good. So reason number 2, why you need to do Mössbauer at as low a temperature as possible is so that these, if I'm at like 80 Kelvin, already like 0.05, that might be closer to even the experimental error of the isomer shift I'm measuring anyway, right? So liquid nitrogen temperature is about the maximum temperature of what's about useful for Mössbauer. I prefer liquid helium temperature, where the second order Doppler shift is basically not even consideration anymore. So higher temperatures lead to a decrease in the experimentally observed isomer shift. So you can only compare isomer shifts at liquid nitrogen temperature or lower. Anything above 100 Kelvin is not generally useful, with maybe the exception of the materials chemists. I'll throw them a bone here. You see that even at room temperature, being about 0.06 different for iron metal or something is not the biggest deal. Okay, so you can compare nanoparticles to nanoparticles, and that's partly why the materials chemists often do Mössbauer at room temperature, much to my chagrin. I don't recommend it unless you're a materials chemist. But even then, I would still argue that it's still better to be liquid nitrogen temperature when you can be. Now, let's look at what does an actual spectrum look like. I'm actually going to admit that this is an incredibly unusual iron Mössbauer spectrum, and that it's an example of a singlet spectrum. We'll see later that the vast majority of zero-field Mössbauer spectra are what we call doublets, and I'll explain why. This was collected at 80 Kelvin. It's an iron 2 hexacyano compound, right? So it's low spin iron 2. And before we conduct a fit, what do we observe? I think one thing I want to highlight from the summer school is that, when I'm doing research, I don't just immediately take a spectrum and start fitting. No. That's not a very good approach to science normally, unless you get lucky. But I'm looking at what am I observing without modeling, and what do I learn? And then I choose, how I'm modeling the data based on what I know about chemistry. And so I can think about the energy range we're going out to plus minus 4.5 millimeter per second. That's an energy range of plus minus 0.002 wave numbers. I've seen that the isomer shift just by eye, that looks to be at about minus 0.2 millimeter per second. We're at 80 Kelvin, so we don't need to worry about our second order Doppler contribution. This is a trustworthy approximation of the intrinsic isomer shift of this compound. This carries information about its oxidation state and its spin state. We'll talk about this later, but the quadruple splitting is apparently about 0. The line width is about 0.3, and it looks pretty much Lorentzian because it's not decaying too quickly into the baseline, so we know the sample is a thin absorber. I see that the transmittance is about 75%. There's really nothing going on in the baseline, so I don't really have like other weird species or something. And boom, now I model the data. You know, first I've investigated what does the data tell me, and then I choose to model it. That's the order of operations. But you know, just from my qualitative model, I knew to minus 0.2, put that into the program for the isomer shift. And then when it freely refines, I at least gave it a good starting guess. I then just blindly hit run. That's what you've got to do. But yeah, that's just a basic example. And it's actually an incredibly unusual one. Because now I'm going to change gears and talk about this phenomenon of the quadrupole splitting. So it turns out that nuclei with more than spin 1/2 have what's called the electric quadrupole moment. This is analogous to the zero field splitting concept of electrons, but we're now thinking about a nucleus, and we call this the quadrupole Hamiltonian, okay? And this quadrupole distorted nucleus ends up having a rotational energy and an electric field gradient, which I'm going to symbolize as this, okay? And what that does then is we end up getting quantized precessions because we're dealing with quantum mechanics. So this excited state, I equals 3/2 nucleus, might be oriented this way, but it might also be oriented along the mi plus 1/2, or the mi minus 1/2, or even the mi minus 3/2. But the point is that the plus minus 1/2 projections onto this axis are different energies than the 3/2. So we get a splitting into two distinct nuclear Kramer's doublets. Okay? But this is analogous to zero field splitting. And this is the origin of the quadrupole splitting effect in Mössbauer, because now from the ground nuclear Kramer's doublet to the excited, we have two different possible energies, a low energy and a high energy. And that's going to lead to two peaks. Okay? And that's what it looks like in the actual spectrum, the low energy and the high energy. And the midpoint between these two peaks will become the isomer shift. Okay? That's what the quadrupole splitting looks like. Yeah, we're going to have to do some math, or you can just trust me. But this is the quadrupole tensor here. This is the summation of the electric field gradient. So this is the electronic part, and this is the nuclear part. And they're going to interact with each other, these two tensors now. And so the quadrupole, I'm going to call this whole thing a tensor, and just write it this way. That's already way simpler. Yeah, and then it's a little bit weird. I'm going to transfer to operator space rather than tensor space and sum up over all of the protons, because only the protons contribute to the quadrupole. And you don't need to follow me for all this, but basically we can start doing some math. And I don't really like being in proton space, so I'm going to use the Wigner-Eckart theorem with Clebsch-Gordon coefficients to transfer to nuclear spin momentum space, and then I'm going to start evaluating and start doing stuff, and we start seeing that EQ pops out from QZZ, and then we keep going, and then eventually we end up basically solving the equation between proton space and nuclear angular momentum space as related by a collection of constants, EQ over I, 2I minus 1. And then we keep going, and we keep going, and we keep going, and then eventually we substitute this result into our Hamiltonian, and we end up here. But we're going to keep going because that's not very useful. This is the full Hamiltonian that contains the x squared minus I squared, but also the xy plus yx and xz plus, and it keeps going because we have diagonal and off-diagonal elements of the electric field gradient tensor, and we have to sum all that up. That's where this comes from. And we keep going because this is a matrix, but we want to have it be diagonalized, so we're only going to call these diagonal elements now the primes and only worry about them, but we can rewrite that in a more convenient form. And then basically it has to be a traceless tensor, and I'm a bit exhausted, but we're already here. And then we can define the difference between x minus y over z as what's called the asymmetry parameter. This is directly analogous to the rhombicity parameter in EPR, but we define it over the range of plus minus 1. This here is way too much math to care about today, but I just want to make the point that it can be derived from first principles, and we end up with two components that matter for my quadrupole Hamiltonian, the z component and the asymmetry parameter. The asymmetry parameter is 0 if the xy directions are the same. The z component is therefore what we call the kind of like principal component of the quadrupole splitting. This is going to really be the main determiner of how big it is. Yep, I already told you about that. The only thing is, unlike EPR where it's defined from 0 to 1/3, in Mössbauer we define it over the range of 0 to 1, but otherwise it's a very similar concept. Now, for iron, the ground state is not quadrupolar, so actually only the excited state quadrupole moment contributes. I'm just going to call that Q, and I excited equals I for simplicity, but we can just plug and chug in everything and eventually with some math end up at this equation. This is probably the equation you've seen in like a Mössbauer textbook. Okay, because only the excited state has this quadrupole effect. There might be other Mössbauer isotopes like nickel where both the ground and excited state contribute, and then you end up with a more complicated expression. But for iron 57, it's actually quite a simple situation. Okay, and you can kind of have a situation where you have two different kind of shapes to the electron cloud, the electric field gradient, essentially. You can have it where the principal component is positive. That ends up giving you a pancake or oblate shape, or it's negative, and that gives you a cigar shape. But the thing is, by Mössbauer, at least zero-field Mössbauer, you actually can't tell the difference between these. So for a zero-field Mössbauer experiment, you're never going to know what the sign of the electric field gradient tensor is. You have to use applied field Mössbauer or slightly sophisticated methods to do that, which I won't talk about today. So yeah, you cannot tell the sign of EZZ from zero-field Mössbauer spectroscopy. Now, if you didn't follow that, that's okay. This is the key expression I just want you to keep in mind. If you don't want to worry about the derivation, that's totally fine. And here's an example of an actual quadruple doublet spectrum. So these are basically ubiquitous. These are extremely common. We observe spectra at Mössbauer. And so here now we're dealing with a high-spin iron 2 hexoxyl complex, okay, in frozen solution. And we see this beautiful quadruple doublet. And again, before I do any fitting, I'm seeing that the isomer shift, the midpoint is about 1.1 millimeter per second because we have peaks at about 2.75 and minus 0.5 millimeter per second. We're at 80 Kelvin, so that isomer shift is good. We don't need to worry about second order Doppler effects. Now I can look at the magnitude and see that that splitting is about 3.25 millimeter per second. The line widths are right at the limit of what I would consider like too broad, but it's about 0.4 millimeter per second. They look Lorentzian in shape. That's a thin absorber. And yeah, basically then when you fit that, you see I did a pretty good job just by eyeball getting good values, okay? In the program today, we're going to be using depth, which is basically 1 minus transmittance, 100 minus transmittance. So you'll see that like the depth of the peak is 20%. That just means about 80% transmittance. So people talk about depth instead of transmittance sometimes, but it's the same concept. Okay, and now the big question is, how do we get the electric field gradient? If you've ever done like electricity and magnetism type physics, you're probably used to dealing with point charges. And you can actually like derive a given point charge Q and like what its electric field gradient tensor looks like. And then you can imagine how that would look for a nucleus interacting with it. We usually like to think about it being diagonalized, so I'm going to orient the primes along Z, so that way I don't have to worry about like theta and phi and all this stuff. And you can basically then work out the X, Y, and Z diagonal components and see, punchline is that for this case, if the charge is along Z prime, then the XY components are both minus Q r to the minus 3. There's no difference in X and Y, so the asymmetry parameter is 0. And then Z is positive and twice the magnitude of the X and Y. Okay, that's what that looks like. And so if I plug that into my quadruple splitting expression, I end up over here. And what I want to show you is that the quadruple splitting contribution dies off pretty quickly. So for Q equals minus 1 at 1 atomic unit, you would expect if it's ln plus Z to be minus 3.2. If it's already at 2 atomic units, see how it's r to the minus 3, it's at minus 0.4 now. So, as you take a atom and you put charges far away from it, the quadrupole effect will start disappearing, okay? Whether those charges are ligands or the actual valence electrons, as soon as they're far enough away, they matter less and less, okay? And you can do that with different point groups, like a D4H type situation, right? Maybe these point charges are approximating ligands. And you can see, right, what these matrices look like along X, Y, and therefore Z. And there's no Z actually, so just X plus Y gives you the total is plus 2 minus 4 in this case. Okay, and you can make, again, quadruple splitting predictions. You can do it for an octahedral symmetry and actually discover that you don't end up with an electric field gradient because you have a symmetric case where all these X, Y, and Z components cancel out. And so, high-spin iron 3, for example, will have a very small quadruple splitting for that type of reason. You're ending up at a very highly electronically symmetric chemical environment, where something like high-spin iron 2 will have a very large quadruple splitting because you have that extra unpaired electron floating around unevenly in that D shell. Okay? So those are 0 millimeter per second. But here's the problem. we don't deal with point charges in chemistry. We deal with electrons in orbitals. So how do we handle that situation? You can basically solve these dipolar integrals considering psi star psi essentially for a given orbital, okay? And you see that there's an r to the minus 3 dependence because here we have r squared and then whatever rx times ry or something, right? But here's, our electronic wave function, and you can see, for example, for a px orbital, what that looks like. For a 3dz squared orbital, what those closed forms look like. And if you solve these integrals for the expectation value of 1 over r to the 3 for 2p, that plays a role. So the 3D has a different, volume it occupies as average r to the minus 3 component. You can basically derive these electric field gradient tensor components. So for a px orbital, it's minus 4/5, 2/5, 2/5. For a dz squared orbital, solving these integrals gives you 2/7, 2/7, minus 4/7. You can do it for fyz squared, whatever orbital you want. In this case, you get minus 3/5, 1/5, 2/5. You have a 4f type contribution. And what I've done is I've gone ahead and just solved all these integrals for you. It took me about a day. Actually, all of these were available for up to the d orbitals, but I went ahead and did all the f orbitals too, which took me a while, but now you'll never need to do it because I did it for you. And I figured I'd throw a bone to the lanthanide chemists out there who might be interested in lanthanide Mössbauer or something. But I want to focus on d electrons, so let's go ahead and plug and chug a bit. And we can think, for example, about looking at 3D orbitals and see, based on the value of Q and a typical 3D orbital being about 5 per cubic atomic units, that we end up at this expression. The valence ZZZ contribution, and then about 8.1 times that, and then the asymmetry parameter comes in if there's some differences in the XY direction. So for example, for a DZ squared orbital, you're going to get about minus 4.62 millimeter per second if you were to populate that with 1 electron. That's what I'm arriving at here, is we can use this expression and add up all the individual contributions for the x, y, and z components and end up at a prediction of the quadruple splitting with just pen and paper. And so we just converted the quadruple splitting using this equation here and plugging and chugging with these guys. So an electron in a pure dx squared minus y squared orbital should give positive 4.6 millimeter per second. But I have to tell you something. This assumes that crystal field theory is correct. But you learned from Serena's ligand field theory talk that ligands are not point charges. We're not dealing with crystal fields, we're dealing with ligand fields. Those are not the same thing. And so there's like orbital reduction and covalency. And you'll see that in real life then, these are actually going to be effectively smaller than what you would predict with a crystal field theory prediction. If you are not dealing with a diagonalized tensor, you have to consider the off-diagonal elements too. So try to orient your frame in such a way that you are essentially only dealing with diagonal elements. You'll have an easier time. So let's look at that practically then. This is really cool because although I can't really tell the sign of the EFG from zero field Mössbauer, I can tell something about the valence electron distribution. So let's look at low spin iron 3, right? Depending on the energetic ordering of my orbitals, so therefore the ligand field I'm in, I might have either 4.6 or 2.3. The magnitude of the quadruple splitting will go down. That tells me something about the actual ligand field I'm in. I'm going to show you a practical example of that in just a moment. High spin iron 3 should be about 0 millimeter per second, right? High spin iron 2 should be 4.6. Low spin iron 2, very symmetric, again, about 0. Okay? These are crystal field theory predictions of the quadruple splitting for different electron configurations, spin states, oxidation states. So the quadruple splitting gives me complementary information to the isomer shift, and it's really those two quantities together that we use to make chemical interpretations of the electronic structure. So let's look at a real example. How about high spin iron 2 hexoqual? Again, that spectrum I showed you, same spectrum. Well, the problem is this. You have a degenerate set of T2G orbitals in our quintet T2G ground state. We have two possibilities then for a Jahn-Teller distortion to get away from that, because nature abhors a degeneracy. We can do an axial compression to a D4H point group and get a quintet B2G ground state, or we can do an axial elongation, again to D4H symmetry, but the energy or orbital energies have changed in ordering, and we get a quintet EG ground state, so now doubly degenerate. And here are the predicted quadruple splittings for a quintet B2G situation versus a quintet EG situation. And I ought to be able to compare that to my experiment and understand what's the electronic ground state I'm looking at. That is a direct application of Mössbauer to electronic structure, and an example of the power of using the nucleus as a probe of it. So, here's our experiment though. Well, 3.2 is like, in between these, so which one do I choose? How do I interpret that? Well, let me remind you of something. These are based off crystal field theory. How accurate is crystal field theory? We can ask Martin Kylverth and Sergio, Serena and Karsten Meyer, because they did this wonderful study of a range of different iron oxidation states in these carbene compounds. And they looked at the formal iron oxidation state as a function of quadruple splitting. So we have crystal field theory predictions in black. We have density functional theory in red, and then we have two slightly different experimental versions of the compound. Now, I would say that if you're calculating quadruple splittings, in general, the theory community considers those to be a lot less reliable and accurate than the isomer shifts. However, the trends are absolutely in line with the experiment, and those are generally trustworthy. But look at how far deviating away the crystal field theory. In every single case except when you predict no quadruple splitting, you predict overestimation, which means that the value you predict is going to be larger than the actual experimental value. And so now if I go back, right, crystal field theory is completely inferior to ligand field theory because you can't pretend that these are not having covalencies. But it gives a good qualitative prediction. If I go back to my experiment, I told you crystal field theory overestimates the magnitude of the quadruple splitting, which means that the only answer is quintet B2G. This is the ground state of this iron hexoqual complex. That tells me I have an axial compression situation for this Jahn-Teller distortion. That's direct structural information, no crystal structure even needed. You can take the crystal structure and see that lines up. That is exactly what happens in this case. Okay, if it were the other situation, the quadruple splitting would be about half the size. Now, the chemical environment, it's not just the valence electrons, but the chemical environment that contributes to this electric field gradient. I have here two iron 2 compounds. Both are low spin because they're dealing with relatively strong field ligands, and yet one, the completely octahedral symmetric case, has 0 quadruple splitting. Yet if I swap out a cyanide for a nitrosyl ligand, I get a huge quadruple splitting. So it's not just the distribution of valence electrons, but rather the chemical lattice, and that's called the lattice contribution to the quadruple splitting. And I already showed you how to get the valence contribution with crystal field theory. This is actually part of the reason why it's extremely difficult, even with like computational chemistry, to get these accurately, is the lattice contribution matters too. And how do you, put a molecule in a lattice? Normally we're doing like gas phase or maybe at best implicit solvation calculations. So that's why a lot of the computed quadruple splittings are a little bit less reliable, okay? But it does contribute too. And because the ligands and surrounding ions also have charges. Now here's another complication. The quadruple splitting may or may not also depend on temperature. And that's a little weird to think about. Why is that? Well, there's a number of reasons, but one of the ones I want to highlight is that the nucleus actually feels an average of electric field gradients of all thermally populated states. For example, if I have a tetrahalo iron 2 molecule, which has a quintet E degenerate ground state that splits due to tetragonal distortion, those states are no longer the same energy, they're slightly different, but the Boltzmann distribution will populate them slightly differently. I get a temperature dependence on the quadruple splitting because those states have opposite sign EFGs. So I notice that as I go from low temperature to high temperature, the quadruple splitting for these compounds goes way down because you're starting to populate the higher state more and more, which has an opposite sign EFG and begins to cancel it out more and more and more. But at low temperature, I'm only thermally populating, one of those, and I'm getting, a good estimation of kind of the intrinsic electric field gradient for a given state. And you can actually use that to look at the quintet E splitting if you model this. So you can look at the variation of going from chlorine to bromine and see that the chlorine has a bigger quintet E splitting than the bromine, which makes sense. Chlorine's a slightly stronger field ligand. You can even swap out tetraethylammonium for paraquat and see actually the counter ion can have a dramatic effect on that quadruple splitting because that's going to also maybe pack and affect the ligand field distortion. And that ends up being the largest in this case, which is kind of interesting. Spin orbit coupling, both in state and out of state, will also perturb this. So you have a lot of potential sources that can cause temperature variations of the quadrupole splitting. Now, I call this the art of fitting reasonable quadrupole doublets, because the minute you have more than one Mössbauer absorber in your sample, life gets more complicated. Because now I have to think about, what am I going to do? I have this hydrogenase cofactor, and I have this model complex, which Sebastian Stroyan looked at with Popescu. And these are low spin because we have all these strong field ligands. But look, if I'm looking at my Mössbauer spectrum, I actually see 1, 2, 3, 4 peaks because there's 2 different quadrupole doublets. These irons are not equivalent by symmetry. They're in different chemical environments, so they have different Mössbauer spectra. But they overlap with each other, right? These 2 peaks on the left are overlapping and give an apparently very broad peak, and then 2 smaller peaks. You might be able to kind of tease out that there are kind of 2 peaks peaking out here in intensity, but you have 3 peaks that are immediately apparent, right? You have 2 quadrupole doublets. Now, I have some options. How do I choose to model that situation if I want to fit this data? I have 3 options, actually. I could model it this way, where I have a green quadrupole doublet modeling these 2 peaks on the left and the purple one modeling the 2 peaks on the right. I could go purple, green, green, purple. Or I could go green, purple, green, purple. How do I know which is good? Well, I mean, if I'm looking at the red, which is the total fit to my spectrum, the sum of these individual fits, honestly, they all look like they fit the data great. So how do I choose? Well, this is where we have to be chemists. We can't just fit a spectrum blindly. We need to think about what's chemically reasonable, not just what's a statistically good fit, but what is something that actually makes sense chemically. And that's where this isomer shift and quadrupole splitting come in together. Okay, so iron 2 is going to have a range of isomer shifts in the high spin state, but also a range of quadrupole splittings. Low spin iron 2 is going to have a different situation. And I can look at fitting each of these doublets individually and seeing, do they line up with something chemically reasonable? Now this compound, if we're smart, we can do electron counting and expect that we should see something of a low spin iron 2 and a low spin iron 1. Okay, we have 2 different irons. So let's look at all 3 models. Model number 1, does my green line up at all with low spin iron 1 or 2? No. No, it doesn't. It absolutely does not. And the quadrupole splittings are too similar. That's not the case, right? Low spin iron 1 and low spin iron 2, they might have a little bit of overlap if you're unlucky, but you might expect actually a bit of a different quadrupole splitting. So the first model is wrong chemically. It's just fundamentally incorrect. Let's look at model 2. We're a bit better, okay? We have at least something that's believable. These ranges are not perfect, but it's believably the purple one is low spin iron 1, and the green one is low spin iron 2. And the same, look at these quadrupole splittings, okay? This is believable. So model 2 looks reasonable. How about model 3? Yeah, maybe even a little better. But I would say, I don't think we can exclude model 2 versus model 3 right now. So actually, we have no idea which of these 2 models is correct. If you want to know which model is correct, you must do applied field Mössbauer. You must. Zero field Mössbauer is not enough. So right now we're stuck between these 2. I want to, before I let you go for like a 10-minute break and we get to part 2 of the talk, tell you that a good fit statistically is not necessarily a good fit chemically. These are both statistically good fits, and they're both chemically good fits. The first model was a statistically good fit, but a poor chemical fit, which is why we excluded it. The chart of typical parameters is helpful, but don't take it too literally. I would argue really these are not, even though model 2 looks a little better, I'm actually going to hint that this is actually the correct model. And so, don't take the chart too literally. If you're slightly outside these ranges, that's not so unexpected. It works maybe 90% of the time exactly, and the other 10% of the time, don't take it too literally. Okay. I want to end the first part of the talk with that. It's really best to try to do a series of compounds. So this was my PhD advisor, John Barry, did this with ACARD, looking at this first example of an iron 5 nitride. And well, actually, this was Karsten. John did the iron 6, but anywho. Yeah, so basically, right, I can look at the correlation of the formal iron oxidation state with the isomer shift and see that they lie almost perfectly on a line in this series of compounds with the same ligands. That's pretty cool. So you can use this as a predictive power then. If you don't have a given oxidation state, you can make a prediction. If I had the iron 1, I predict that's going to be somewhere out here as an isomer shift. Okay? Iron 6 is going to be somewhere over here. It might be negative even. And so, yeah, I can actually compare these series of compounds and see that the iron 5, which is slightly negative, almost 0, has a different isomer shift than the iron 3, and that's pretty cool. They're both low spin. Okay, I'm going to let you go for a 10-minute break.